Welcome to this video on regression lines, predictions, and residuals. By the end of this video, you will be able to make predictions using a regression line, keeping in mind the dangers of something called extrapolation. You will also be able to calculate and interpret a residual, and you'll also be able to interpret the slope and y-intercept of a least squares regression line. So you will need your calculator today, so make sure you've got it with you. The directions say we're going to go to Stacklet, but I want you to be able to do this in your calculator so you can use it on your test. The first step that you're going to do is you're going to input this data into your calculator. Now I want you to notice for 5 rubber bands they do not have a distance traveled, so I do want you to skip this one for right now. We're going to come back to it, it's part of our problems. So you're going to go to your calculator, press the Stat button, go into Edit, and you'll enter the number of rubber bands into list 1 and the distance traveled into list 2. When you're done, come on back. Alright, so we have our data put in. Now we want to calculate the line of best fit. So you already know how to do this. This is where correlation and the correlation coefficient is that we were looking at the other day. So press your Stat button. Go over 1 to calculate, okay? And then we're going to go down to number 8, okay? So I want you to notice that there are 2 linear regressions, one at number 4 and one at number 8. The one at number 4 is the more traditional form that you will have seen, and that is think y equals mx plus b, where a is the slope and b is the y-intercept. Stats people like to write their linear equation lines in the form of a plus bx, where a is the y-intercept and b is the slope. And the reasoning from that is we're talking about real-world scenarios that start at the y-axis and then change as they go to the right from there. So you're adding or subtracting from the y-axis. So that's why they like to use that one instead. So we're going to choose number 8. You should have put your data into list 1 and list 2. Go all the way through, calculate. Now, we have our information. So the other day we were talking about the correlation coefficient. So this is a strong positive linear because it's 0.999. It's almost a perfect one correlation. R squared we're not going to do anything with for right now. Now we have A and B here. Notice in your equation you also have A and B. You're literally just going to take whatever A equals and substitute it into the equation where A is, and take whatever B equals and substitute it into the equation where B is. So we're going to write it in that form. So we're going to have our regression line is y equals 25.333 plus 7.464x. So I just took the values from A and B and substituted them in. Alright, so you might be thinking, well, what is a regression line? A regression line, so this is something called the least squares regression line. It's the most perfect line that will fit right in the middle of the data. So approximately half of the data points are above the line and half of the data points are below the line. So that's the one we always want to use, is the one that our calculator will give us. Alright, so we have our line. So we can use this regression line to make predictions. So in number 2, let's predict how far Barbie would travel in her bungee jump with 5 rubber bands. Okay, so rubber bands, remember, was an x value. So we're going to plug it in where the x goes. So we're going to say y equals 25.333 plus 7.464, and our x value that we're interested in is 5 rubber bands. You do need to show your setup. Pretty much anything we do, you're going to have to show your setup so we can see where everything's coming from. So when you put this into your handy-dandy calculator, you should come out with 62.653. And this is in centimeters, so we're going to go ahead and add centimeters to the end of this. So that will be our predicted distance traveled with 5 rubber bands. Now, in reality, one of the group members found the measurement for 5 rubber bands, and the actual measurement was 64 centimeters. Was the prediction from the number 2 too high or too low, and how far off was it? So what actually happened is he had 64 centimeters of drop, but we predicted 62.653 centimeters. So we had a difference of 1.347 centimeters. So was the prediction too high or too low? So 64 is what actually happened. The prediction is less than 64. So the prediction was too low. It was low, I will say, by 1.347 centimeters. So the prediction was low by 1.347 centimeters. And we just got that number, remember, what actually happened minus what was predicted to happen. Okay? So now what I want you to do is pause the video, and I want you to, for number 4, make the prediction for 20 rubber bands. And would you trust this prediction more or less than the prediction you made in number 2? Once you finish answering that, go ahead and come on back and we'll talk about it. So when I inserted 20 for my number of rubber bands, because 20 was number of rubber bands is an X value, I came up with 174.613 centimeters would be the distance traveled. Okay, so the second part of this question is, would you trust this prediction more or less than the prediction we made for number 2? Number 2 was for 5 rubber bands. So when I looked at the data, we tested, and this is just like we did with our water balloons, from 0 rubber bands to 7 rubber bands. We didn't test anywhere near 20 rubber bands. So I feel less confident about this, less trustful, because it is a lot more rubber bands than we tested with. All right, ran out of room. That's okay. I was less trusting because that's a lot more rubber bands than we tested with in the data that was collected up above. All right, so what is the y-intercept of the equation? Remember I was telling you that we wrote the equation in a plus bx form because a is the y-intercept and it's a real world, so everything builds from where it begins. So your y-intercept is 25.333. Okay, and what does it mean? Okay, well, at the y-intercept, what is your x value? Your x value is 0. So in this context, what does that mean? 0 for x would mean 0 rubber bands. All right, so we'll say when we used 0 rubber bands, the distance traveled was what? It was 25.333 centimeters. Okay? And now we're going to talk about our slope. That was the b value. Okay? So what is slope? In this case, the number for it was 7.64. And how do you get slope? What happens each time with your slope is every time your slope changes, it's because you're adding 1 rubber band. Okay? So when we added, take this so you can see it. when we added one rubber band, the distance traveled increased by, because we had a positive slope, 7.464 centimeters. So when we added one rubber band, the distance traveled increased by 464 centimeters. All right, so I'm going to go back and kind of add some more information in. This is like your note shell. Let's add on to it. So one thing I want you to remember is when we come up here, we're going to start back at number 1. When you're going to write a regression line, you're predicting what's going to happen, not what actually happened. So how we notate that is we put this little caret on top of the y, and what that means is that's y hat. He's wearing like a little wizard's hat, right? So that's y hat. And y hat means predicted. So if you see something that says y hat equals, you know that's not an actual value, that's a predicted value. So that means your predicted y. And I'd really like you to get into the habit of, instead of using y and x, inserting in their actual context. It'll make this a lot easier as we go along. So instead of y hat, what's being predicted is the distance traveled. So we're going to just say distance here. And it's a predicted distance, so still put a hat over it, equals 25.333 plus 7.464, and x is the number of rubber bands. When you add the context in there, it just makes it a lot easier, especially when you start having to plug different things in, because sometimes you plug in a predicted distance and have to solve for the number of rubber bands. So that just helps you remember where the location is. Okay. So in number 2, so instead of y, it would have been it's a predicted distance. So we're going to go ahead and put distance equals 62.653 centimeters. That just lets any reader know that this number is not a real number, it's a predicted number. Okay, it's like we used our magic 8-ball. So in number 3, we want to know how far off were we. And so this is something called a residual. You just want to know how far away the prediction was from what actually happened. And to find a residual, you're going to always take what actually happens and minus the predicted from it. So your residual, remember AP, like AP stats, residual equals actual minus predicted. What actually occurred minus what was predicted to occur. And the difference is kind of like an error, and the error we call it a residual. Okay, and so the prediction was low by 1.34 centimeters. So it could have gone the other way. We could have over-predicted too. It just depends on, each line is a little different depending on the data that's being put into them. Okay, so here I had you make a prediction for 20 rubber bands. Now think about this. This is kind of what we're doing with our water balloons when we go outside. We're going to make a prediction for a number of rubber bands that's much further than what we were testing for. So I'm less trusting because this is way outside the area that we tested. This is something called extrapolation. And extrapolation. And extrapolation is dangerous. So I want you just to mark that down. It's dangerous. Okay? because you're not going to be as accurate the further outside of the range of the data that you collected. So making an extrapolation is not a very smart move, but we're going to do it anyhow with our water balloons as part of the fun. But in regular stats, you're not going to be extrapolating. You would want to change your data interval if you could then. All right. So number 5, we talked about the y-intercept. So the y-intercept is where x is 0. So you kind of look at it like that. And so you will be asked to predict or to interpret your y-intercept, because that's what stats does. We're all about interpreting what's going on. So we did a pretty good job on this one, and I'll formalize it a little bit more on the back. But so when we used 0 rubber bands, we talked about that. That's your y-intercept. That's where x equals 0, so it's the y-intercept. And notice that they included context here too. Okay, so you don't want to just write x equals 0. It's x equals 0 context. Okay, and then your distance traveled is the actual number on the y-intercept. Okay, and we have some context here because we included the units. All right, and the last thing we talked about was slope. Okay, slope, remember it's the change in y divided by the change in x. All right, so our slope was 7.464. So when we added 1 rubber band, so 1 rubber band, so when x increased by 1, the distance traveled increased by this number here, which is our slope. Okay. Now, is this what actually happens every single time? Is it the same number every single time? It's not. It changes a little bit. This is really kind of an average number. So instead of just distance, I want you to insert right here in front of distance the predicted distance. Okay? So same up here with our y-intercept. When we use 0 rubber bands, the predicted distance traveled. So right there you want to put predicted also, because this isn't actual, this is what's just being predicted to do. It's an average over time. All right, that was a lot of information. I'm going to summarize this down some and get it down to some chunks for you, and then have you try to check your understanding. All right, so on the back, I have 3 things I want to tell you. I think the first one, we can go, say about there. A little narrower. For the second part, almost in half, I think we can do, it like that. Let's make it a little bit wider. Hopefully you didn't draw it yet. I don't think that's quite going to work. Need just a little bit more space. All right. So our big ideas. The big thing that we talked about here was predictions. To make a prediction, you need to have a regression line. So we're going to say y hat equals a plus bx. Okay, so this right there, that's your predicted value. The a is your y-intercept, and your b is the slope. Okay? You got to include your hat when you're writing this out, because that means predicted. One thing I want you to be sure that you pay attention to is to be careful for extrapolation. Be careful of extrapolation. An extrapolation is making predictions outside the interval of x values used to collect data. So an interesting thing there, we talked about 20 rubber bands for Barbie, how that was an extrapolation because it was far outside our 0 to 7 rubber bands. Your Y-intercept can also be an extrapolation depending on where you collected your data range at. And so sometimes your Y-intercept can seem funny and not have a lot of meaning to it. In our case, we actually collected data on x equals 0, so that wasn't a problem. But sometimes your Y-intercept can even be an extrapolation because your data is far from the x-axis. All right, residuals. Your residual, remember, is your actual minus predicted. And I'm going to tell you how to interpret it. So I'm going to give you these kind of math libs where you just have to plug in some numbers and some context, and you're sure you're formatting your answer in the right way. So we're going to have the actual, and then you're going to put whatever your Y context is in here. I don't want you to write when you're answering. Do not write the words Y context. Put what the problem is about, the Y values right there. So the actual Y context was whatever your residual is. And then you have to decide, is that number higher or lower than the predicted whatever the predicted number or your X context was there. So the actual, whatever your Y context is, was the residual number higher or lower, you're going to pick one, than the predicted X number for that X in the X context. So on the other side, I'm going to flip it back over, we had a residual here, and our actual distance traveled was lower by 1.347 centimeters than the predicted distance traveled for 5 rubber bands. That's kind of your context. It's giving you kind of a framework to work in so you're sure you have all your information. All right, and then we're going to give you the interpretations for your Y-intercept and slope. So Y-intercept, when x equals 0, so you want to give that context. When there's no rubber bands used, is what we did on the front. When x equals 0 in context, the predicted whatever y is, Y context, the predicted distance traveled is whatever your Y-intercept is. Okay? And include, if there's units, include the units on there. And for slope. Oh, and that in units. So slope. With each additional whatever your x context is, the predicted y context will either increase if it's a positive slope or decrease if it's a negative slope by whatever your slope is, and include the units. Okay, so with each additional whatever x context is, the predicted y context, it will increase or decrease by the slope. So with each additional rubber band from the front, the predicted distance traveled increase by 7.464 centimeters. Okay, so what I want you to do is try these problems on your check your understanding, pause the video, and then come back and check your answers. Alright, here is your answers. To interpret your slope, the slope was 40. With each additional week, the predicted increase in male rat weight is 40 grams. Part B, does the value of the y-intercept have meaning in this context? It does not. Well, no, it does. The y, because we did measure around when the rat was 0 weeks old, and so the predicted height at 0 weeks is 100 grams. To predict the rat's weight at 16, I'm predicting weight, so I've got weight hat. Plugged in 16, I got 740 grams. The residual, if the rat actually weighed 700 grams at 16 weeks, I take what actually happened minus what was predicted, and I got negative 40 grams. The actual weight was 40 grams lower than the predicted weight at 16 weeks. And finally, should you use this line to predict a rat's weight at 2 years old? No, we should not. We only collected data to 25 weeks, which is 6 months. 2 years is way far away from 6 months. So I went ahead and calculated it out, and I'd get 4,260 grams, which is 9.38 pounds. That's a gigantic rat. I would not have confidence. 2 years is far from the collected data of the first 25 weeks. This is an extrapolation. Hopefully that was helpful. Let me know if you have some questions. See you in class.